I'd like to introduce our next speaker. Professor Keith Worsley is from McGill University, Department of Mathematics and Statistics. He did his degrees at the University of Auckland in New Zealand. So Canada's been quite successful in attracting talent from New Zealand. I didn't mention Terry Peters was also from New Zealand. Did you know each other when you were back there?
We certainly knew each other at McGill.
Oh, okay. So you met at McGill. Keith is also a member of the Royal Society of Canada, which is not a small task. That's quite an honor to achieve. And his current interests are in the application of random fields to brain imaging and cosmology. He's going to talk about statistics today. Welcome, Keith.
Thanks very much. Thank you very much for the invitation. I feel a bit nervous actually because I'm not an image processing person at all, and here I am in a sort of trying to show some images in front of a room full of experts. So I'm really not. It's not my main interest is in statistics, and I thought rather than sticking to those lousy handouts that you've got in the thing there, everyone else seems to be deviating a bit from these things, so I thought I'd deviate. Well, just that, they asked me just for some handouts, so I just copied. I put some of my stats ones through a scanner and then sent them to Jeff, and I realized that maybe it's better not to put so much stats in, so I'll sort of forget about most of those, and I'll just show you the main ideas instead. So, in fact, I thought I'd start off with, in the handouts. I started off with a new type of experiment called Bubbles, which is one of these face recognition experiments. And I thought I'd start off with this cosmology instead, because it actually sort of fits in a little bit better with what I want to talk about. So here it is. This is this is the motivation for it. It's a study of galaxies in the universe. The Earth is here, right? And this is one slice through what was called the Centre for Astrophysics survey. It was the first very deep survey, redshift survey of galaxies. And what they got out of this, and what they recognized, is that there's some sort of really large-scale structure going on here, that the galaxies do not appear to be randomly scattered in the universe, and that there seems to be, they seem to form clusters and sometimes strings of galaxies like this, and sometimes sheets of galaxies. And so they were trying to sort of deal with this in a statistical way. And the method that they used, I'll show it to you later, is the Euler characteristic. And I'll give you an example of this in a moment. And so this is going to be the sort of guiding principle through my talk. It's all going to be about this Euler characteristic. In 3 dimensions, it just counts number of blobs, if you like, minus number of handles plus number of hollows, interior hollows. And here's some examples just quickly so that you can see what I mean. There's the donut, for example, is 0 because of the hole in the middle counts as -1, and the pretzel would be -2 for the same reason, and the tennis ball would be +2, right, because you've got the hollow bit inside, so you'd get +1 for that. So I'm going to use this Euler characteristic as a descriptor of the shape, if you like, of these galaxies. It's exactly the same technique that they used in this paper, by the way. I think they might mention it's in the title there, Topological Analysis, and that's exactly what it refers to. So let me just show you the data. This is kind of fun. It took me a little while to do this, but this is a silly thing, really. This is supposed to be the sun here, and this is supposed to be the Earth going around about the sun. It's not to scale, as you can see, but I thought I'd put it there so you at least get an axis of. So we're sort of looking down from the North Pole, and here's our own galaxy like that, you see. So you can see it's got spiral arms like that, and the sun is in this little very short. Our own solar system is in this very short spiral arm just here, sort of actually fragmentary. This one was discovered just recently, a couple of years ago. Of course, the reason why they don't discover these things is because that your view of the galaxy is edge on like that, so that it's extremely hard to discern what the 3D structure is. Now, these other blobs that you see around it are other galaxies which I haven't bothered to try and render in the same sort of fashion. I just represent them as blobs, although the size is correct. This one was discovered about 3 years ago, I think. Again, hard to see because it's actually on the other side of the the center of the galaxy, so it's obscured from us by the galaxy center. And then this guy was discovered just recently, about, I think, last year, or maybe early this year. It's actually almost touching our own galaxy. One thing that I found when I did this is that galaxies are actually quite close together compared to stars. Stars are actually very far apart, compared to their size. But galaxies are, quite a bit closer together, so that in relative terms. So what I'm showing you here is our local cluster of galaxies. It's a bit hard to see, so what I'll do is I'll make all the galaxies the same size. There you go. So now you can see them a little bit easier. In fact, our own galaxy, there's about 40 odd in the local cluster, and our own galaxy is the second largest. It's actually quite a big one. And just to locate it a little bit, I'll just move this off so I'll locate it. I can put here it is. It's this one here. So I'll just put the axes on so you can see. There it is. So that's where our own galaxy is there. Okay, so now we come to the CFA redshift survey. First of all, I'll just tidy this up a little bit and get rid of our own galaxies. It helps with the rendering a little bit. And then I'll just I'll switch on our own galaxy. I think that does the trick. And then I'll just sort of back off. Whoops, hang on, let me turn it. There you go. There it is. So I'll just turn it around. You can still see our own galaxy cluster there, right? So it gives you some idea. And here's the CFA data. There it is. It's like that. And I'll just try and make that a little bit. I'll just make that transparent so you can see through it. I think that does the trick. Yeah. So there you go. Now that's just part of the. Is this going to come back on again? Was it? No. Nope.
Which side was it on?
That side. Oh dear.
Feels pretty hot. We can go now.
We don't have I've lost the overhead projector.
Yeah.
Yeah, usually it's the computer that goes, isn't it?
It's technology.
Old technology doesn't work.
Maybe if we.
What do we do? Any ideas?
Pull it out from in here, maybe. Because it feels
Give it a
pretty
shake.
Keith, I can wave it around up here and see if I can project it on.
Yeah, that's right. Yeah.
In the meantime,
Well, actually, I got some of it in the. I think all my slides are in the handout there, but yeah. Oh, that's really sad, isn't it? What do we do?
we'll see if we can get another projector.
You want to see if you can get another
I
one?
mean, they're all over the place, so it shouldn't be so hard.
Okay. Density here, which is on a Gaussian scale. What they do is they transform they first of all take those points that you saw over here, and then they smooth them with just a Gaussian filter. They give extra weight to the undercount. Oh, here comes one. Okay.
Oh, I thought you fixed it.
No, I was just.
Should we just take the whole thing down?
All right. So I'll get rid of this one. It does smell extremely hot, this thing. Yeah, it's probably cut itself off. There you go. Well, this plugs it down. Hey, business now. This on here somehow.
This one is at a different height, though.
Is the fan running?
That's it.
It's a fun side. It's great. Good.
No problem. Well, this is wonderful. It's actually better than the other one. It's brighter, isn't it? It's better than the other one. Yeah. Okay. So now I'll carry on. Okay. So there's the. Now where was I up to? Euler character. Yeah. Smooth galaxy. So what they do is they just smooth this data with a Gaussian kernel, and then they convert it all onto a Gaussian scale, so that 0 corresponds to like 50-50 density, and then +1, which I've set over here, corresponds to sort of halfway through. So there you can see the thing thresholded at +1. And the main feature of this across the... another one. Give me that one as well. Two. Triple projection. Okay. So the main feature that you can see in this is what they call the Great Wall, which is this huge kind of sheet of galaxies that extends, right across the most of the survey region. The little blob here is actually coming from our own galaxy, our own local cluster of galaxies. Then there's a big void here between this and the rest of it. And if I just twiddle the threshold a little bit, you can see, how the whoops, I just got a little bit too far there. You can see how the Great Wall sort of does extend right across the visible region. So what they're interested then is to try and capture this in some numerical fashion, and they use the Euler characteristic to do it. And so what I've got down here, written at the bottom, is the Euler characteristic of this set. And it's +20. And then, of course, as you increase the threshold here, it'll start to, whoops, that should be, I'm twiddling the wrong number here. I'll just keep that there. That should be -135. I actually just get flustered and you hit the wrong button then. So if I increase it a little bit like this, you'll see that the thing decreases. Now the Euler characteristic is +13 and so on. And if I send it down here, so the sort of negative thresholds, then it starts to become negative because now there's lots of little tunnels, if you like, which are inside the search region. So it's making the Euler characteristic strongly negative. So what they do with this then is that they... oh, by the way, and just in case you're interested, how am I doing this? It's the only little bit of C code that I wrote in this software was that I wrote something to work it out like that. It's just the same way that Euler would do it, just counting points and edges and faces which are inside the high-density regions, and that's how you actually work the thing out. And then, so it's quite easy then just to sort of do this for all possible thresholds, and then they draw a graph like this, and what you see on this graph is the threshold along here, the Euler characteristic up there, and then the jagged line here is this one here is the observed Euler characteristic for the CFA survey. Now, what I've superimposed on that is the same thing for random galaxies, but I just simulated the whole business. And then they use the discrepancy between what you observe and I'll show you what it looks like for random galaxies, just so you can see smooth random galaxies. It looks something like this. Come up in a moment. Or maybe it already has. Yeah, I think it's come up now. So if I go back here, and you see that the Euler characteristic is changing. So random galaxies looks quite different. If I set it back at +1, you can see that the feature that we saw before, the Great Wall, doesn't appear at all, and the thing breaks up into a lot more little pieces. So the neat sort of theoretical result is that they're able to get an expression for the expectation of this Euler characteristic over all random repetitions of this kind of experiment. And the formula is kind of quite neat. I'll just show you. It's actually in the handouts. And I'll show you what form the formula takes. So here's how it looks. It's so if you have a normal Gaussian distributed, what we call a random field, which is isotropic, it looks the same everywhere, and it's smooth, and it has a standard normal distribution at each point. Then the expected value of this Euler characteristic is given by this very simple formula here, which is it's just a Hermite polynomial times e to the -1/2 x squared. So in this case, d is 3 dimensions, so it's x squared minus 1. So what's fantastic about this result, it was derived by Robert Adler from the Technion, one of Ron Kimmel's colleagues, about 20 years ago, is that it gives you an exact expression for something that seems on the face of it very, very complicated. It's a random topological quantity, but it turns out that you can actually find an exact expression for that thing. That's the Euler characteristic per unit volume. It's like sort of density of it, if you like. Now, since we're in a finite region, which is this jelly-shaped thing here, the survey region, then you need to modify it slightly for the boundaries. you can see what's going to happen is that as you can see over here, for example, the excursion set does bump into the boundary of the search region, and that alters the topology of some of the components that do that. And so there's a simple expression for doing this, for allowing for this, and it goes something like that, if you've got now a finite volume rather than infinite space, then it's just a sum of these, what are called intrinsic volumes or Minkowski functions. Again, I think Ron Kimmel mentioned something about that. There's a formula for them. It's sort of a little just to show you that a formula does exist. But these things are multiplied by the same Euler characteristic density, but in different dimensions, added up over the number of dimensions. So you end up with a formula like this, which now allows for the finite extent of the search region. And it's got 4 terms in it. There's the volume term, a surface area term, a sort of diameter term, and a sort of point term at the bottom there, which all add up and contribute to this expected Euler characteristic. And so that's what appears on that graph that I showed you over here. This is this one over here. So that's the smooth line that you see there, is that expected Euler characteristic worked out, and that's exactly the number that's printed down the bottom here, like here. Get the idea? So as I twiddle the threshold here, and I change the threshold a little bit, then you should see that you observe 73, you expect 61, and so on. If I set it higher, you observe 58, you expect 42. Of course, there's some kind of discrepancy between what you observe and what you expect, but it's in pretty good agreement as you go through. So now if I switch back to the real data, not just the random stuff, then you can see that there's some evidence of a discrepancy. You can see it on the graph as well. There's kind of a difference between those 2 things, and when the stuff eventually loads, you should see the change that, yeah, it's already loaded there. So now what happens is the observed is a lot less than the expected. So if I bring the threshold down to, say, where it was before, then you observe 26, you expect 51. In other words, some of these tunnels have disappeared, and you get a kind of a clumping of the data, and so that's why, due in fact to that great wall structure that appears right across the galaxy survey. Does that seem okay? So just to update that, this is data that was from 10 years ago, and now they've carried out a much more ambitious survey, which I'll just show you the new stuff. It's the Sloan Digital Sky Survey. There's a telescope out in Pasadena which is doing nothing but photographing the sky all night, and they're going to try and construct a galaxy survey which extends much further than the CFA one. And the first year's data of that has been released, and you can it'll come up in a moment, I hope. It'll come up in a minute. It's quite large, and my poor old computer is struggling to load the stuff in. They're going to cover the whole of the visible sky eventually, but I think the project is due to run for 4 years. And yeah, there it is now. It's appeared. So I'll just show you what the new stuff looks like. It's and I'll set the threshold of this one to there, and you should be able to see it now. There it is. So this is the new survey, or at least part of it. It's like a sort of like a chunk, if you like, a slice like that. But you can see that there's an enormous amount of stuff in there. There's structures, huge things like this one here, which are almost just as big as the Great Wall that we saw before. And then buried inside there are other equally enormous features that seem to be common throughout the universe. And again, you can play exactly the same trick, and you can compare the observed Euler characteristic to the expected one. And again, you find that there's a big discrepancy between one and the other. And you observe 466, you expect 774. So again, there's evidence of severe clumping. Okay, so what's all this got to do with medical imaging? I'll maybe just get rid of all this stuff completely, and I'll show you the application to medical imaging. So let's get rid of all of that. Let's bring up, this guy here will do the trick. So let's take a look at some fMRI data. Now you've seen some of this already, so I'll just put this slide up so just to remind you. 3D data. The subject was lying on the scanner and given an alternating hot and warm stimulus to the right leg sticking out of the scanner. And we're interested in correlating the stimulus with the observed fMRI data to try and localize the parts of the brain that respond to the painful heat stimulus. And you can see, one of the time courses at one particular voxel here, and the alternating hot and warm stimulus. And the t-statistic for the correlation is quite high at 6.59. At other points, of course, it's a lot lower. And our task then is to try and select those regions which show significant activation and screen out the false positives. Okay, so how does the Euler characteristic come into that? Here's exactly the same slice. Of course, it's 3D data, and I can sort of twiddle this in 3D. I can put the brain on so that the outer brain on roughly so that you get an idea of the location of the slice. And let me just move the thing out of the way a little bit down to the bottom so it doesn't get in the way. So there you see the stuff rendered there. And let's threshold the data. That's the first thing to do. If you pick the usual threshold for 5.05 significance, you end up with something that looks like that. In other words, you get apparent activation almost everywhere in the brain, which is clearly wrong because even if there was no activation at all due to the painful heat stimulus, then you'd still expect 5% of the image to look like that, right? Just because it's a 0.05 test. And so again, clearly we have to raise the threshold in order to compensate for, searching such a large space. And the question arises, where are you going to put the threshold? Should we put it here? Should we put it up here? Where are you going to stick the threshold? Now, this is where the Euler characteristic comes in a strange way. What I've written down the bottom there is the observed Euler characteristic and the expected Euler characteristic, just as I showed you for the galaxy data, right? And the idea behind it is this. If you're at a very high threshold, like say 4.6, then the Euler characteristic is kind of counting the number of blobs, because all the hollows and the handles have disappeared, and what you're left with is just isolated pieces, of which there should be 11. I mean, you can probably try and count them if you want. There's 1, 2, 3, 4, 5, 6, 7, 8. I can see 8 already. 9, 10. Oh, there it is. The 11th one's down there. So there seems to be 11 of these guys. So if at this particular threshold, if it was just pure noise, you'd expect to see 0.116 of an Euler characteristic. In other words, 1 time out of 10, you should expect to see anything at all which is present in this image. And so this gives us the solution then of where to set the threshold. The idea is that we now try and increase the threshold in such a way that we bring the expected Euler characteristic close to 0.05. I think I hit it just exactly right. So, do you get the idea? So at this very high threshold of 4.78, you would expect to see 0.05 of an Euler characteristic. In fact, you see 10. But at 0.05 means that 1 time out of 20 you might see something, 19 times out of 20 you'd see nothing. So this expected Euler characteristic is a device for enabling you to set a threshold on these random images. I mean, just to sort of drive the point home, if I put in random data like I did for the galaxies, I think I've got that down here somewhere. T-stat for random noise only. Here's just pure noise. Then at this very high threshold, you see nothing. So, I mean, if I lower the threshold a bit, then of course you do see something, just as we saw before. But if I put it back at that 4.78, then you see not. And the idea is that 19 times out of 20 you would see nothing here at all. 1 time out of 20 you would see something, and so that gives you a way of setting the threshold. So perhaps I've convinced you after all of this that we can use this expected Euler characteristic as a device for thresholding these random fields. That's more or less exactly what I just said. There are asymptotic results for this this probability of ever crossing the threshold, but they're really poor. And it turns out this expected Euler characteristic is really accurate, even though it's a strange way of calculating it. And as I stressed before, there is an exact expression for that, but there is no expression whatsoever for this thing here, which we're really after. So there's the main thing. So what I'm going to do then for the rest of the talk is just give you some applications of this to different parts of medical imaging and just show you how it goes. The first one I'll show you is one on cortical surfaces. Let me just get rid of this guy and bring up, here's the data. This is some ancient data that I got from Jason Lurch, who's sitting here in the audience. Let me see, which one is it? This guy here. This software, by the way, is called Iris Explorer. It used to be a free giveaway with the Silicon Graphics workstations. I think it first came out 10 years ago, but it's still really fantastic stuff, I think. And you don't have to write any lines of code. It's just join things together with little wires, as you saw in that sort of flow diagram that I had before. Okay, so here's the data set. It's 321 normal adults, and thanks to Jason, extracted the cortical surface on each of these and measured the cortical thickness in millimeters right down the brain, and that's what you see here. And just the real purpose of this study was aging, but just for a joke, I looked at see if we could see any difference between males and females in terms of cortical thickness. And so the first step before you do any analysis is to first of all put all this onto the average cortical surface. This cortical surface, by the way, is really neat. Each subject has exactly the same number of triangles, and all in roughly the same position. So to get that average cortical surface, I just had to average point-wise the coordinates on 321 subjects. And the remarkable thing is that it still actually does look like a brain, rather than... In fact, you can see all the main features there, including the fact that this bank of the central sulcus is thinner than this one over here. It's kind of really, it's really neat. Okay, so if we're going to do any stats on this, the first thing we will do is to look at the average thickness of first of all, the males. So that's the average thickness, millimeters. And then, see if I just get this right, come here. The average thickness of the females, and then the difference between them. We can work out the standard deviation. That's the usual, two-sample pool standard deviation for a t-statistic, and here's the t-statistic itself, which is the ratio of the difference to the standard deviation. Just the usual, nothing fancy here at all. It's just the usual standard, the usual thing we have in an elementary stats course, but worked out at every point on those 321 subjects. So anyway, there's the results. You've got evidence here with a very high t-statistic of increased cortical thickness in males compared to females. And if I just turn the thing over here, you can see underneath here that there's regions, particularly in the frontal lobe, where females seem to have thicker cortex than males, just in this region here. So again, what we want to do is to try and set a threshold on this. I mean, where are we going to put it? If we put it again at the usual, 1.64, you get something that looks like this. You see stuff all over the place, but of course you'd expect to see that anyway. You expect 5% to look like that, just due to random noise. So the trick is then how are we going to do it? Well, it turns out that the formula I just showed you, you can still use it. It's perfectly good. If I just dig it out of the pile here. In fact, I think it's sitting over here on this side. You can still use this thing over here. The only difference is now the volume is 0, because it's now a surface rather than a 3D object. And the only thing you've got to work out is the surface area, the caliper diameter, and the Euler characteristic. This turns out to be 0, and this turns out to be +2. And the main term is this one here. But the formula is so good that it doesn't even, you can even apply it to very strange shaped search regions. In this case, a cortical surface rather than a solid object in 3D. Now, there's one more story to this before I kind of finish, and that is that you might remember that the conditions for this magnificent result to be true is that the data has to look isotropic. And again, I'll see if I can pull the slide out, which has got that piece of information on it. I should just throw them all on the floor and see if I can. Maybe it's the one. Oh, yeah, no, I don't think so. I've lost the down. Oh, yeah, here it is. This is the one here. So one of the conditions for this theory is that the data has to be isotropic. In other words, the data has to look equally smooth everywhere. And it turns out for this, well, first of all, it's hard to define isotropy when you're dealing with data on a surface which is convoluted in that fashion. And secondly, when you do work out the effective smoothness of this data right across the surface, then it's highly non-isotropic. There's different regions, like for instance here, where the data is apparently smoother than it should be, around about 20 millimeters. And there's regions inside here where the data is not very smooth at all. And so strictly speaking then, this theory doesn't apply because it does require this condition of isotropy. I can tell you the reason why, but I won't go into I'll skip the details of that. So one idea that I had to try and overcome this was the following. Well, maybe we can actually do something. We can deform this surface and work on a different surface in such a way that the data becomes isotropic if it were to be embedded in 3 dimensions. And the idea behind it is the following. If we want to try and make this data equally smooth everywhere, why don't we take the little edges down here where it's too smooth and shrink them together to try and make it rougher? And why don't we take the edges down here, which are where it's very rough, why don't we sort of blow this out in order to try and make that a bit smoother? Do you get the idea? Okay, so, I mean, the idea being that, if I just, again, what I want to do then is to try and reset the edges on this mesh so that the edges are have a length which is inversely proportional to the smoothness. So this is a kind of multidimensional scaling, but on a very grand scale. It's sort of a local version of multidimensional scaling rather than a global version. And there's no neat solution involving eigenvalues and eigenvectors. You just have to do it by iterative methods. So let me quickly show you the results. Looks something like this. Yeah, that's the one. So I'm just sort of linearly sliding between one result. Actually, I'm going to turn it over like this because it actually makes more sense to look at it from underneath. I'm just linearly sliding from one solution to the other. So what's happening is that these regions where it's too smooth are now being shrunk to try and make them a bit rougher. And it's trying hard to blow these out, but it can't. So it's crinkling the surface and making it sort of crinkly. And so eventually you end up with something that looks like this. Luckily, it still looks like a brain, just. But now if you recalculate the smoothness on this new surface, then it becomes equally smooth everywhere. Well, it's not quite equally smooth. If I were to twiddle the color map, you'd see that the smoothness is not perfect. And in fact, what occurred to me was that if you had more dimensions, like 4 dimensions, then you could sort of pop the surface into a 4th dimension, right? And you could readjust edge lengths again in the same fashion, and then to try and get a better sort of equal smoothness everywhere. That wouldn't affect this result because all these higher dimensional terms, like the volume and the 4th dimensional volume and so on, would all still be 0, so it wouldn't affect this, but you might get some sort of better approximation to this thing here. And one thing that occurred to me is, how many dimensions do you need? I mean, 5 dimensions, 6 dimensions, where are you going to stop? And well, it turns out there's a Jonathan Taylor found this result out for me. There's a neat result called the Nash embedding theorem, which says that the number of dimensions is finite. I don't know if you ever saw it. Did you see the movie, what was it called? Beautiful Mind. Remember that? And there's a point in The Beautiful Mind where a guy comes up to John Nash and says, congratulations, you've won the Nobel Prize. And he says, that must be from my embedding theorem. Because he considered that to be his finest piece of work. And as you know, he won it for his work in game theory. But anyway, the embedding theorem, Nash's embedding theorem, says that the number of dimensions is finite. And in particular, you only need 5 dimensions to achieve exact isotropy for this data. So anyway, that's just to show you that it does in fact work. So we can go ahead and use this thing here, but the extra dimensions don't contribute anything because they're all 0, but these are the ones down here that do the trick. So having gone to this trouble here, we can now put the t-statistic happily back onto this surface. There it is, and we can now threshold it, work out the expected Euler characteristic, and the threshold, I'll cut a long story short, it tends, I think it's about 4.4, maybe not, 4.35, something like that, 4.35, so that you control the expected Euler characteristic, again to be 0.05. And so these are the regions which are p less than 0.05. This is the stuff that you can write up in the Journal of Neuroscience and publish as the regions where the brain is thicker in men compared to women. I mean, I could put the whole thing back onto the average cortical surface and just so you can get some better idea of it. That's 4.35. It seems to be these regions at the back here in the visual area, and there's also this region here. I'm not quite sure what that is exactly. Maybe someone here knows it better than me. It also seems to be in the other hemisphere as well. So those are the regions which, and the similar regions for the negative end of it for the where women have higher cortical thickness than men. So anyway, that's just to show you the theory. In fact, is the calculation of these coefficients. In fact, turns out not to depend on doing this nifty multidimensional scaling at all. I haven't got time to go through it, but it's actually in the handouts that have been printed for you. There's a neat way of doing it which doesn't involve any of this multidimensional scaling at all and just requires, in a nutshell, replacing the three-dimensional coordinates of these points by the 321-dimensional normalized residuals. I mean, I haven't got time to go into the details, but it's an easy way of doing the calculations, and it's not hard at all. Okay, so that's the end of this little one here. Unless there's any questions about that. Shall I hit the button? Okay. So, further extensions to this. Here's the non-isotropic stuff. I'll skip all of that. It's in the handout, but I'll just move on to further extensions. What have we been doing since then? Well, we've had all sorts of other ideas about this as well. There's a thing called scale space, which yesterday's speaker talked about wavelet transforms. This is like a continuous wavelet transform where we try varying the amount of smoothness in the data. And the reason for this is that the astrophysics people, for example, are not... I mean, I did tell you that they smooth the data, and the question is, how much do they smooth it by? And the answer is they try a whole range of different amounts of smoothing, and they redraw those same curves. This is from the Astrophysics Journal. Different amounts of smoothing, and the idea of scale space is to actually add the amount of smoothness as a sort of an extra fourth dimensional parameter to the data. And again, I haven't got time to show you an example of that. That's the one involved with the bubbles data, which is in the handout. Now we've tried something called rotation space, and actually, this a little anecdote about this one. I went to one of those conferences in France. I think Ron Kimmel was there too, and afterwards was invited to Thomson Aerospace to give some kind of presentation. And they were kind of interested in this stuff because it allows you to detect randomly rotated objects in a field of background noise. And the first author on this is my colleague Khalil Shafi from Shahid Beheshti University in Iran. So it's kind of an interesting thing. He did all the theoretical work on this thing here. So this is useful at detecting objects which have unknown rotation as well as unknown scale and unknown location. We've also looked at some non-Gaussian fields as well, chi-squared, T fields, F fields, and Hotelling. I want to give you an example of Hotelling's T-squared before I finish off with the last one on correlations. This is useful for multivariate data of the type that. I'll show you the example that I have in mind. But before I do that, I'll show you the example I have in mind for this. It's some data on that I got from one of my colleagues in Rome on subjects who, I'll just fire it up, so we'll wait for the thing to come up. Here it is. It's subjects who had some sort of brain trauma. There was no blood, that's why it's called non-missile brain trauma. But they were in a coma for several days, and when they woke up out of the coma, they gave them an MRI scan to look for anatomical damage. And so to do that, we compared the whole group of these non-missile trauma patients with a group of 19 age and sex match controls. And then we extracted these vector deformations that were needed to warp each subject's brain to an Atlas standard. And so here's the, well, first of all, here's the outside of the brain. This little thing here is some kind of artifact. I'm not quite sure what that thing is exactly. It's nothing to do with the missiles or anything like that. It's an artifact of the rendering. But you can see inside, there's the whole thing. Because we don't want to look at that. We want to look at we want to look inside the brain. So we'll get rid of the skull, and this is just a thresholded white matter mask, and we want to look inside there. And here's in the slice at the bottom here is just one of the slices that the deformations are based on. So here's the actual deformations from a single subject. They look like this. Oh, I've got to switch it on, that's right. There you go. There they are. I'm not showing you all of them, it's actually more finely sampled than this, but that gives you some idea. And so these, as I say, these are the little vector deformations required to move this subject to some kind of Atlas standard. So we've got these vector deformations then worked out for each of our 36 subjects for the 17 trauma patients and the 19 controls. So the first thing you'd want to do is just look at the average deformation. In fact, we saw a picture of average deformations this morning, right? I think this morning's presentation, the mouse brain had a. Okay, so here's the average deformation, trauma average. There you go. So you can see that there seems to be quite a bit of movement, if you like, inside the brain here. Also some stuff down the bottom, but of course we should compare that to the average for the trauma that's the trauma average. We should compare that to the control subjects, which are down at the bottom there. And now this is still here, but the stuff in the middle has disappeared. So now let's look at the difference between the two, which is this one here. And so what you see is that most of the movement, if you like, in brain structures is round here in the center of the brain. Okay, now in order to detect that statistically, we can work out Hotelling's t-squared. There it is. It's the sort of Mahalanobis distance, if you like, between the average of the average deformation for the trauma and the control group, worked out at every single voxel. The S matrix there is the 3x3 variance covariance matrix. So let's take a look at the Hotelling's t-squared. So here it comes. Yep, it's loaded in. And again, we've got the problem of where to threshold it. If you choose the usual 0.05 point, then you see complete garbage, just something like that. What we really need to do is to increase that threshold to compensate for the multiple comparisons. And how do you do it? Well, the answer is that you replace those Euler characteristic densities, those Hermite polynomial things, you replace it by this guy here. I just put that there to show you there's a nice, neat, closed form expression with no approximations. It looks a little nasty, but it's easy to program it up. These are finite sums, they're not infinite sums. So there's an exact expression for this thing. So you just put that thing in instead of the Hermite polynomial business. And so then you end up with I'll jump right to the threshold. It turns out to be 54. So if you jump to the 54 threshold, now for some reason the Euler characteristic is this guy here. Okay, yeah. So the threshold gives you an expected Euler characteristic of 0.049. And so there's the damage p less than 0.05. And what's kind of neat about this method is that not only are you able to localize where the damage is, You can also see what direction it is too. So you can zoom in on this and take a look around here. You can see that the movement is always in the outward direction like that for the difference between trauma and control. So it seems to be like that all the way around the object. The movement is always away from the center. In fact, what's happening is that the boundary between the ventricles and the white matter is moving outwards. You could say it's due to swelling of the ventricles, but I've been told it's more, the correct explanation is atrophy of the white matter surrounding the ventricles. Why should that happen? Again, I've been told that, because you'd expect, these are car accident victims, right? You'd expect the damage to be around here. How come you don't see anything up here? And the answer is that apparently if you're in a car accident, you get some sort of twist on the head is knocked, and you get a twisting of the brain, which puts a lot of tension on the brain stem, where it connects to the brain itself, and that apparently causes the atrophy that you see. So I've been told. I don't know. Terry, what do you think? Does that sound reasonable? Well, there's actually also a little bit of damage down here in the brainstem. Look at that, which perhaps would fit that hypothesis. But it would be nice if they could record the direction of the blow to the head, as well as so then they could actually look. We could look in certain places, but that information is not available to us, so we just have that. Okay, I've almost finished. Perhaps I'll just quit this one here. I want to show you one last one before I finish. I hope you don't mind, because we did start a bit late with the overhead projector business. Okay, so I want to show you one last thing, which is more generalizations of this whole thing. Is this idea down here, correlation, what we call correlation random fields. The idea here is that we've got pairs of points, and we're looking at the correlation between something measured at one point and something measured at another point, searched over all possible pairs. And the application that I have in mind for this is, again with the help of Jason, a study that we were involved in multiple sclerosis patients. And here's the outline of the study. There were 425 patients with mild multiple sclerosis with lesions in their white matter. And so we were able to measure the lesion density, and we were able to measure the cortical thickness. And the idea was that if you get a lesion in one part of the brain, you might see atrophy of the cortex in nearby cortex, sort of downstream from the fiber connections. Because it would, if you're cutting off neuronal impulses to part of the cortex, then you'd expect to see that cortex shrinking. So what we did was we tried to look at the correlation between lesion density and cortical thickness at every pair of points, and search this whole thing for big ones in the negative sense. Let me show you the data. I should have perhaps warmed it up first. I'll show you the data so you can get some idea of what's going on. Again, we used, with Jason's help, we managed to extract the cortical thickness on these 425 subjects. It takes about 40 hours of computer time. Is that right, Jason? Where's Jason? Yeah. Is it something like that? Something like 40 hours of computer time to get one cortical surface? Okay, so technology has improved and it's very fast now. So this will come through in a moment, I hope. Yeah, thank goodness for that. Okay, so here's again one subject in the database. Just happened to be the first one that I pulled out, actually, and I was kind of lucky because it tells the story of what we're trying to show. You'll notice here in the visual cortex, it seems to be a lot thinner on this side than that side, right? Now, let's take a look at the lesions inside the brain. So let's peel away part of the brain, and let's take a look inside. And you can see there's a lesion right there. You see it? Well, of course, the lesions have been smoothed, so I'll decrease the threshold so you can see more lesions. I'll bring it right down to about here, a little bit low. But what happens is that there's a lesion. You see that one down there? It's right nestled inside there in the white matter, right next to that piece of cortex. So the hypothesis is that the presence of this lesion right here is cutting off neuronal signals to this cortex and causing it to atrophy. Okay, so that's the idea. So what we want to do then is to, on these 425 subjects, is to work out lesion density and cortical thickness at every possible pair of points, and look at the correlation between them like this. This is actually averages, but it just illustrates the point that as you have more lesions, you get less cortical thickness. So what I'm going to show you now is a thresholded image of these correlation coefficients. Here the correlation is minus 0.56, but you'll see that there's some, okay, so I'm going to, okay, let me put the thing, I'm rushing against time here, so I'm flustered. Okay, let's put everything onto the average cortical surface like we did before, same old trick. And let's move straight to the negative correlations. So there they are. So that's the maximum negative correlation of one point on here with everything inside. And there's some quite big negative correlations, as big as minus 0.57. But what we're really interested in is seeing which particular ones are the big ones. So let's look at the top 100 of these guys. Here they are. There they are. Great, everything's working. So what have I got here? Let me just improve this a little bit. Let me just change the rendering. There you go. See the brain a bit better, and let me just make these little blobs transparent so you can look through them. Okay, so what have I got here? Each of these little arrows here is linking together a point in the white matter with a point on the cortical surface over here. And the color on that arrow is the correlation, the negative correlation on this color scale here. So what this is saying is that presence-absence of lesion here at this particular point in the white matter has a minus 0.55 correlation with cortical thickness at that point on the cortical surface. You get the idea? Okay, so again, how do we deal with this in a statistical sense? We have to set the threshold, and the threshold again can be worked out in exactly the same fashion using random field theory. You can figure out what those Euler characteristic densities are. I'll just flash this up. It's just this again, just to show you there's a formula for it. You can set that equal to 0.05, solve back for the threshold, and the threshold turns out to be 0.325. And so that's in fact, determining the threshold was crucial to doing this, because you have to know the threshold before you do the calculations, because you can't keep all of these correlations. There's just too many of them. So you have to know the threshold in advance, just keep the big ones and throw the small ones away. And so that's how I did it on my laptop, by the way. It just took a couple of hours. It wasn't too long. And now, the sad thing about this, which is driving Arnaud crazy, is there's too many of them. I'm only showing you the top 100, but in fact, there's 25,000 of them. And Arnaud has been I'll show you a few more. You want to see a few more? I'll show you another. Arnaud has been staring at these things there's the top 300. If I put all of them in, it'll crash the graphics card. But Arnaud is having an enormous struggle trying to make sense of this thing. But all I can tell you is that these are all significant, p less than 0.05. And I'm only showing you local maxima too, by the way. Just again, to cut down the number of arrows, I'm just showing you local maxima there. Okay, I think I better stop there. But I thank you very much for your...